So let's look at formal charge. So let's do nitrate. Okay, good, cool. So I'm just going to go through the entire process of how to do this Lewis structure, just so we can get a little bit more practice, right? So the first thing I want to do whenever I start a Lewis structure is I want to figure out how many valence electrons I have, right? Total valence electrons. So nitrogen comes to the table with, this requires participation on your guys' part, sorry.
5, right?
5, yep. So nitrogen has 5 valence electrons. Oxygen comes to the table with 6 valence electrons, and there are 3 of them, right? The negative sign out here means that we have to have 1 extra electron. Everybody all right with me there?
Oh, we add 1 more.
Yes. So anytime you have a charge on the outside, ugh, it's taking so long. Please be better. Okay, cool. So anytime we have a charge on the outside, right, we have to add an extra electron to our total. Right, so our total valence electrons would be 18 plus 6, 24. And then we take nitrogen, we're going to put it in the center, and we're going to have all of our oxygens attached with single bonds to start. We want to subtract the bonding electrons from the total electrons. So I've used 2, 4, 6 electrons in bonding here. So I have 18 electrons left over. And I'm just going to start putting them around the outside of the molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18, right? So I've used up all of my electrons, and I'm good to go electronically, right? So what's my next move?
Bring one of those pairs like on an oxygen and make it like a full octet for nitrogen.
So we see that nitrogen only has 2, 4, 6 electrons around it, so that's not a full octet. So we're thinking we're going to need to share electrons in a double bond here, right? So I have this is going to be my new structure, right? Cool with me? So everybody has a full octet here, right? So octet rule is satisfied. We've used all of our valence electrons, so this is an acceptable Lewis structure. Right? So the next thing we want to evaluate is this the best Lewis structure? So what kind of things do we want to consider when we're asking whether or not it's the best Lewis structure?
Is this like the lowest amount of energy it can have?
Mm-hmm. Yeah, but specifically, what are the qualities that make it lower energy? Anybody want to help her out? Sorry.
Are there any like formal charges?
Yes, exactly. We want to evaluate for formal charges. Right? Specifically, what do we want the formal charges to be?
Like that minus.
We want, yes, so we want them to equal the, silly phone. We want them to equal the charge on the nitrate ion, right? But we also want them to be minimized, right? Meaning we want the smallest number of formal charges possible. Does that make sense? Hopefully it does. So, with formal charges, I like to draw in all of my electron guys because this is a different way of counting counting electrons than when we do for the octet rule. Now we're not considering how many total are bonded. We're just looking at how many are directly around each atom, right?
Okay.
Yeah? So if oxygen came to the bond with 6 electrons, right? That's what we said up here, 6 electrons. And here it has 1, 2, 3, 4, 5, 6 electrons around it. It has a charge of 0.
Okay.
Cool?
Mm-hmm.
Now we can look at nitrogen, right? How many Sorry, give my phone a second. So how many electrons did nitrogen come to the table with?
5.
5. So nitrogen came with 5 electrons. And how many does it have directly around it here? 4. So my overall charge on nitrogen is +1. Does that make sense? This is just how we do formal charge evaluation. So when I subtract the electrons it has around it from the amount that it came with, right, I see that I have a deficit of 1 electron on nitrogen, aka a +1 charge.
Okay.
Now let's look at my other 2 oxygens. So again, we said that oxygen comes to the table with 6 electrons, right? And how many does it have around it here?
7.
So I have 6 electrons minus 7. So what's the charge on this oxygen? -1. Right, so I have a -1 charge here and a -1 charge here, right? So I have 2 negative charges and 1 positive charge, right? So what is the net charge? -1, right? Which is what we wanted because that's the overall charge on nitrate. Does that make sense?
So where do you put that, or do you not put it in the net charge?
So the way we would, so I'm gonna turn the page so I can clean this up a little bit. So I have a positive charge here and 2 negative charges here, right? Yeah? So is this the least number of charges that this molecule can have? Could we make less charges? And if so, how? What did you do to get nitrogen to have a satisfied octet?
We added an extra bond.
Yeah. So if you have a negative charge here and a positive charge here, right? Negatives are attracted to positives. Right?
Right?
You with me?
Yes.
So if there's extra electrons here and not enough electrons here, then couldn't we just move this lone pair into a double bond to get rid of those charges?
Okay.
So let's try it out. Right? Sorry, my phone will catch up with me eventually. There we go. So now nitrogen has 1, 2, 3, 4, 5 electrons around it, right? So no more positive charge. This oxygen has 6 electrons around it, no more negative charge, right? So now I have a negative charge here. Do you see how this structure has less charges than this structure?
Yes.
So this
when you start off with with nitrate, you have NO3 minus. So you'll always end with 1 minus.
No, absolutely not. No.
Okay.
So this is a trickster. Okay, I'm doing this one on purpose because I know that while this looks like a charge minimized structure, right? What's wrong with this structure?
Well, it has 10 electrons around the central atom.
Exactly, right? This has nitrogen exceeding the octet. Who's able to exceed the octet?
4.
Has to be row 3 and below, right? So if I'm in row 2, I cannot exceed the octet rule. Okay? So even though this is a charge minimized structure, it's not a valid Lewis structure.
So how do you know who exceeds and like when drawing Lewis structures?
You just told me, right? You said there's 2, 4, 6, 8, 10 electrons around it, right? That's an exceeded octet.
Oh no, I meant which elements.
Oh, that's what we were just talking about, right? So if you're in row 2, you can't. Never, 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 ever, ever, right?
Anything below can?
That's correct. So these guys are able to have your exceeded octet.
Can you give an example of exceeding octet?
Yeah, absolutely. Before we move on, though, we can definitely do an exceeded octet. But before we move on from this problem, let's talk about the geometry. Okay? So we agree that this guy is not the correct structure because we exceeded the octet here, right? So when we talk about this guy, electron geometry, right? We have 1, 2, 3 attached atoms, right? So what is my electron geometry? Mm-hmm. And we have no lone pairs, right?
Mm-hmm. So it's the same.
So the molecular is the same. Right? Does that make sense?
Yes. Yes, so the hybridization would be sp2.
sp2, yes! So I think one of the things that that students really struggle with in the hybridization is that the explanation for hybridization is really long-winded and pretty complicated. But what you really need to know about hybridization is just this, right? If you have trigonal planar electron geometry, then your hybridization is sp2. That's it. Does that make sense?
Yes.
So, yeah, it seems kind of daunting to be able to understand what's going on and why it's happening, but this is really what you need to know. The trigonal planar and sp2 are the same, right? Hybridization matches the electron geometry. Okay. Any other questions about this one? We're all right?
Yeah, we're good.
Okay, so then let's do an exceeded octet. Let's do this guy, right? What's that guy's name? Sulfite! Yay! Made me happy. All right, so sulfur comes to the table with 6 valence electrons. Oxygen comes to the table with 6 valence electrons. There's 3 of them. And we have a -2 charge on the outside of the molecule, so we need to add 2 extra electrons, right? So I got 18, 20, 26. Is that right? Yeah? I did math. Yay! All right. So now I have sulfur with 3 oxygens around it. So I've used 2, 4, 6 electrons in bonding, and I've got 20 left over, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Huzzah, I used all of my electrons. So what's the first thing I want to evaluate?
The formal charges. Octet?
Octet, exactly, right? So all of my oxygens have 2, 4, 6, 8, right? And sulfur has 2, 4, 6, 8, right? Sorry, I was moving my pen, but you guys couldn't see it. So the octet rule is satisfied, right? So we're good to go.
Yes.
Cool. So next thing we want to do is formal charge, right? So we have the octet is satisfied. So now we want to check for formal charge, right? So after doing a lot of these, what you'll recognize is that you'll start to see patterns in terms of what these guys look like and what the charges are, right? So we have our oxygens are all the same, right? The way we have them drawn. And oxygen came to the table with 6 valence electrons. And here all of our oxygens have 1, 2, 3, 4, 5, 6, 7 electrons, right? So each one of my oxygens has a -1 charge. Right? Now what about sulfur? How many electrons did sulfur come to the table with?
6.
6 electrons, and how many does it have here?
There's 5.
5.
5.
So then I have a charge of +1 on sulfur, right? Everybody all right with that? So then, is there a way that I can minimize the formal charge?
Yes.
How would I do that?
Borrow the electrons from the other oxygen.
Yeah, so I want to take one of the electron pairs off of, or one of the lone pairs off of an oxygen and share it with sulfur, right?
Excuse me?
Yes.
Why do you need to do that?
Because we're trying to minimize the formal charges, right? We have 1, 2, 3, 4 charges here, right? And the overall molecule only has 2. So we're trying to see, can we make these charges, some of these charges, go away? Does that make sense too?
Okay.
Yeah?
Because we sorry.
No problem.
Like the total of the charge is still negative to.
Correct. So the total of the charges has to be the total of the charge on the polyatomic. Otherwise, we would have the wrong number of electrons for the structure. Does that make sense?
Yes.
Perfect. Great questions. So we have the correct number of electrons, right? But what we want to see is, can we make some of these charges go away? If we have a negative charge here and a positive charge here, and I'm just singling out this one arbitrarily, right? I could have been talking about this one or this one, right? But the negative charges are going to be attracted to the positive charge, right? So these guys want to go towards this positive charge to get rid of it, right? They're attracted to each other. Does that make sense? Cool. So now when we redraw our structure, right, these guys still have negative charges on them, right? You with me? But now sulfur has 1, 2, 3, 4, 5, 6 electrons, right? No charge on sulfur. And this oxygen has 1, 2, 3, 4, 5, 6 on it, right? Do you see how this is a charged minimized structure?
Yes.
Cool. Now we want to come back to the structure and recheck that our octet rule is still satisfied, right? Because if we don't recheck that, we might have accidentally broken the octet rule, right? Just like we did on the nitrate ion previously. So here we have 2, 4, 6, 8, 10 electrons around sulfur, right? But sulfur is right here in row 3. So it's allowed to exceed the octet. Does that make sense? You with me? Kinda, sorta? Cool. So, in this case, the sulfur is allowed to have up to 12 electrons around it, right? So this is the maximum number of electrons, right? Whoops, sorry.
Is that for every element that exceeds the octet?
That's correct, yes. So any element that's exceeding the octet can have a maximum of 12, right? So 8 is our minimum and 12 is our maximum, right? For some elements, the ones in row 2, these 4 guys, right? They're never allowed to exceed the octet rule, which means that 8 is their maximum, right? Right? But any of these guys can have 8 minimum and 12 max. It's ugly and you can't see it, but whatever. Does that make sense, guys?
Yes.
Cool.
Yeah.
So, electron geometry.
Tetrahedral.
Tetrahedral, which means the hybridization
SP3.
must be sp3, right? Oops, sorry. And our molecular geometry
Trigonal pyramidal.
Is trigonal pyramidal. Does that make sense, guys?
Yeah.
Awesome. I'm going to stop the video real quick.